My name is David Tarbotton, for those of you who don't know me, and Mike asked me to come today to talk to you about snowmelt and snow energy balance modeling because over the past, I guess, 10 years or so here, I have, with my graduate students, developed an energy balance snowmelt model. Last class, I understand you sort of covered the basics of the energy balance. So what I'm going to do today is lead you through the through some of the details of the snowmelt model that we've developed. So I'll be mostly going off these PowerPoint slides, and you should have handouts of them, and I guess they're being shared remotely. The model was developed firstly by, I guess, master student Tanvir Chowdhury, and a PhD student Tom Jackson worked on it, and Charlie Luce worked on it. Many of us all at the water lab. I guess somebody else has just dialed in. And the objectives behind developing a snowmelt model were to give a physically based calculation of the snow energy balance. So we wanted to use the physical principles that you've learned about to actually calculate snowmelt. We were interested in simplicity. We wanted to represent the snow in terms of a small number of state variables. We started out with the intention that the model be transportable. It's always a nuisance if when you apply a model at some other place, you have to recalibrate it. So the properties of snow should in principle be the same from place to place. So if it can be transportable, that's nice. Based on the reading of the literature, we decided that the diurnal cycle was important. So we had to model at a time step shorter than a diurnal cycle. And the model was designed to match the overall accumulation and ablation of the water balance. And it was also initially designed for erosion prediction. That's because we were funded on a project for erosion prediction. And the idea behind keeping it simple was so that we could apply the model over a spatial grid, so it would become an explicitly spatially distributed model. So if you only have a model that's got 2 or 3 parameters, you can do something like that. If you've got a really complex multi-layered model, then that becomes a hard thing to do. This just lists some of the papers that have been written that sort of describe this model, and you can get those all from my website, and I understand that Mike has probably given some of them to you already. But I guess we're not going to go spend all our time on papers, so it's time for show and tell. Brought a tiny marvel of a single snowflake. This is from Kelvin a few years ago. I think we might learn a lesson from how this utterly unique and exquisite crystal turns into an ordinary boring molecule of water, just like every other one when you bring it into the classroom. So maybe we should go outside for a bit and see the beautiful snow crystals that are on the ground. Maybe we should be there instead of up here, but instead we're going to be talking about snow energy exchanges. This is a slide that you saw last time, and I put this up because you'll see a very close connection between this and the way we represent the processes in the model. You've got the fluxes, the solar radiation flux, the long wave radiation flux, sensible heat, latent heat, ground heat flux, heat brought with precipitation, a change in the energy content within the snow, and the meltwater flux. And there's the snow involved. There's a thermally active soil layer that's communicating with the snow in terms of transferring heat. I guess the thing that you'll see different about this slide, it's got much more impressive graphics than mine. This is this slide sort of gives the model physics and parameterizations used in the UEB snowmelt model. And I've sort of broken it up to where at the top we have the inputs. It's designed as an energy balance model to take inputs of solar radiation, the water vapor content of the air in terms of vapor pressure, the air temperature, precipitation, and wind speed. Now that is quite a demanding set of input requirements. Many people actually desire a model with fewer input requirements than that. Specifically, the humidity and wind are quantities that aren't measured at all that many places, so sometimes people want to have a model that just has sort of air temperature as its input, or air temperature and precipitation. But we thought it was important to have the wind and the humidity processes represented in the model. The incoming solar radiation, we do have ways to estimate if it's not measured based on the sun angle, the season, and the time of year. So those inputs are connected. Well, this just shows sort of the arrows that connect them. The net radiation is the incoming radiation minus what's reflected, which is the incoming shortwave times the albedo. The incoming long-wave radiation is calculated based on the air temperature and the humidity. You probably learned last time about sort of black body radiation and the principles of emissivity. And the emissivity of the air is usually related to the water vapor content. Then the heat that's brought with precipitation is related to the precipitation and the air temperature. And then we have fluxes that play a role in the energy balance equation, but also depend on the surface temperatures. So where on the left here we have these arrows only going in the downward direction. On the right, these arrows go both in the downward and the upward direction because the properties of the snow surface affect these quantities. The sensible heat flux is a function of the air temperature and the snow temperature. The latent heat flux, the amount of evaporation or sublimation from the snow, which takes with it energy because it requires energy to translate water molecules from solid phase to gas phase, is a function of the vapor pressure in the air, how dry the air is, as well as the temperature at the surface, because the temperature at the surface controls what the vapor pressure is at the surface. And then there's an outgoing long-wave radiation, which is only a function of the temperature at the surface. Then all of those fluxes had better balance with the flux into the snow by basic conservation of energy. And then at the bottom of the snow, there's perhaps meltwater outflux that is presumably infiltrating into the ground, although it might be running off beneath the snow. And you also have some ground heat flux. We keep track of state variables that give the energy content and the snow water equivalent of the entire system, snow as well as the soil, over an effective depth. And our model is primarily going to be concerned with how those state variables advance or change in time. So this just shows the sort of numerical modeling structure of the model. And here basically it says we're looking at how the snow water equivalent and the energy content of the snow change with time. And snow water equivalent changes with precipitation, melt rate, and evaporation. Basically, this equation says that the rate of change of time of the snow water equivalent is equal to the precipitation minus the melt rate minus the evaporation. Precipitation adds to the snowpack, melt, outflow, and sublimation take away from the snowpack. In this equation, we do not distinguish whether precipitation is rain or snow, because we say all the water gets added to the snowpack. If it's in the liquid phase, it will bring energy with it that might cause more water to melt, and it'll end up adding to the liquid water content of the snow, which if that gets large enough will drain out of the bottom. So rain gets added and then perhaps drains out or perhaps refreezes depending on the energy state of the snow. Then we keep track of the energy contents. So the rate of change of energy content with time is all the energy fluxes, net radiation, incoming long wave, heat with precipitation, ground heat flux, outgoing long wave, sensible heat, latent heat, and melt out flux. And we can just write this in a general form as these are functions of the state variables, W and U, as well as the model inputs. So once you've set it up like that, one can use a fairly standard numerical technique to advance this model in time. And we use a predictor-corrector algorithm because the amount by which these fluxes change in time actually depends on the surface conditions. So you don't want to only use the surface conditions at the beginning of the time step to say what's occurring during the time step. You also want to consider what is happening during the time step. So we take our sort of first guess, if you will, the first prediction says the snow water equivalent at that, or at the end of the time step is the snow water equivalent at the beginning of the time step plus this rate of change from F1 times the length of the time step. And then we use a corrector approach. We take that prediction, we put it back in this equation here, remembering that these state variables actually change some of these fluxes here. And we apply this model again where we use the average of the fluxes at the beginning and the end of the time step. So that's what we've got here. F1 at the beginning plus F1 prediction divided by 2 gets added. And that we take as our sort of final estimate of how the state variables have changed by the end of the time step. This just goes into a little bit more detail, showing some of the processes involved. So here I've got the external forcing quantities that we spoke about before, the solar radiation, incoming long wave, and heat with precipitation. The input data that we provide has to basically provide that information. Then we've got the actual equations for the surface temperature dependent fluxes. So you probably saw equations similar to this last time for calculating the sensible heat flux and the latent heat flux. Basically it calculates the fluxes as a bunch of coefficients here that involve things like the latent heat of vaporization, the gas constant, the density of air, the heat capacity of air. But the most important term is a gradient. The sensible heat flux is proportional to an air temperature gradient, and the latent heat flux is proportional to a vapor pressure gradient, the difference between the vapor pressure of the air and the vapor pressure at the snow surface. Notice these K terms here have the wind speed in them. So you need some energy in the wind to actually transport water vapor and transport heat away from the snow surface if you've got the convective fluxes active. Then the outgoing long wave radiation is, again, this is a sort of Stefan Boltzmann black body radiation type equation. It's proportional to the surface temperature to the fourth power. And then we have fluxes into the snow. Now, this top equation is one of the interesting parts of this model. We don't keep track of the temperature of the snow as a state variable per se. If you remember on the previous slide, I just had water equivalent and energy content. Well, this equation shows how the energy content is related to the temperature. Basically, if the energy content is defined relative to 0 degrees C, the melting temperature in the solid frozen phase. So if the energy content is greater than that, the amount of water that energy can melt is present in the snow. If the energy content is less than that, the temperature will be below the freezing point, and the amount it's below the freezing point is based on the heat capacity of the snow, the water equivalent times the heat capacity of snow times its density, as well as the ground below that's also involved with the snow. So we are thinking here of an average temperature of the entire snowpack and some ground below that. Am I supposed to be switching to the instructor camera at all, or is he doing it? I don't know. Doesn't matter. Then one of the interesting things, or what is unique about this approach, I guess a lot of the models that had looked at this problem before had tried to sort of build layers into the snowpack, looked at the sort of top 5 centimeters, the next 10 centimeters, and made a lot of layers so you can keep track of the heat as it moves around within the snow. That's important because snow's thermal conductivity is fairly small. You probably all know that snow's a good insulator. So the surface temperature is different from the temperature down below, yet here we're representing it with a single temperature. I didn't want to have to go through the effort of trying to model all the detail of the within snow processes. Firstly, because I thought it was complicated, and I wanted to see if we could get away with just keeping it simple. So we just made a single snowmelt model, but we said we're going to allow the surface temperature to be different than the temperature down below, and we're going to use the concept of the depth sensitivity to the diurnal temperature fluctuation. There's well-known equations based on the conduction of heat into a semi-infinite medium that says how deep a oscillation at the surface penetrates. If you've got a high frequency oscillation, the depth to which the rapidity with which it damps as you move down to the surface follows an exponential equation. So we just took a length scale that's related to how that fluctuation attenuates and said, I'm going to calculate the conduction into the snow as a gradient over that length scale. And then the coefficients in the front here are the density of snow, the heat capacity of ice, and a thermal conduction parameter. And you can sort of group these all together to define a surface conductance, which is this Ks term here. And then I'm going to write the energy balance equation at the surface, and I'm going to specifically note which of the terms depend on surface temperature. The sensible heat flux, the latent heat flux, the outgoing long-wave radiation, and the conduction into the snow depends on the surface temperature through this equation we've constructed here, and the energy content as well as the snow water equivalent, because they give you the temperature from the primary state variables of the model. So now this becomes an equation. When you put all these other equations into it, it's a fairly long, messy equation, but it's a closed equation, and one has to solve it for the surface temperature. The idea being that the surface temperature is going to adjust itself so that the conduction into the snow balances the energy inputs from above. If there's more sunshine, the surface temperature will tend to rise so that there's more of a gradient into the snow, and that energy can be conducted in. If the sun sets and you have outgoing long-wave radiation, so there's a loss of heat from the surface temperature will fall so that there's a gradient that can then suck heat out of the snow. So the idea is that the surface gets into equilibrium between the above the surface forcing and the conduction into the snow. So one just basically solves this equation, and it's a nonlinear equation, so you basically linearize and iterate. It's a fairly standard Newton-Raphson solution procedure, and the equation is well enough behaved to converge really quickly. There's one exception, or the key exception is if you get a solution that says the temperature of the surface of the snow is greater than 0 degrees C, that's non-physical, because snow cannot exist at greater than the melting point. What that really means is that more heat is being supplied at the surface than can be carried into the snow by conduction. So if that's the case, the extra energy is going to go into generating meltwater at the snow surface. that meltwater is going to infiltrate, and that will effectively carry energy into the snow by the meltwater infiltrating. If it encounters cold snow at depth, it'll refreeze and therefore release its latent heat that it got from the surface. If the snow has become isothermal, it'll pour all the way through and drain out of the bottom. So if we get from this solution the temperature greater than 0, we just set the temperature equal to 0, and the additional energy is vectored downwards, and it's just added to the total energy of the snowpack, because we're not worrying about where the energy is within the snowpack. So it was that sort of device that allowed us to keep a single layer model and represent the as well as represent the insulating properties of snow. This slide just shows how the model was modified to account for forest canopy. This is a very simple approximation to account for forest canopy. Basically, we just have a density of forest canopy parameter FC, and we reduce the incoming radiation, we reduce the net radiation, the solar net radiation, and we also reduce the turbulent transfer and outgoing radiation terms by those expressions there, and apply the equations in exactly the same way. Some snowmelt models actually try and keep track of meltwater being generated at the surface and then sort of penetrating through the snow, and they sort of talk about the depth of a wetting front and a kinematic wave process as it sort of penetrates down and drains out the bottom. I wanted to try and avoid having to do that because it's a really complicated process, and I don't think it follows a sort of orderly wetting front type of system. If you there've been studies done where people have put dye on snow, and they see it's a really sort of a fingering type of process. You get ice layers developing, and the paths that meltwater takes to actually flow through snow are really complex. So the approach we took was we said we're not going to worry about any of that. We're just going to look at how much water there is in the snow and assume it drains according to the sort of Darcy's law for flow through a porous media, and the hydraulic conductivity being proportional to the relative saturation cubed, which is one of the relationships that comes out of the Handbook of Snow. I guess Sam Colbeck's work has established this sort of thing. So we first calculate the volume of liquid water in the snow. We calculate the relative saturation, which is the liquid volume minus an amount that's just held in capillary retention, that's a parameter, relative to the pore volume. So this is a number that's going to be quite a lot less than 1, because the snow's pore space never gets filled completely with water. And then there's a saturated hydraulic conductivity parameter. And as the liquid volume of the snow increases, the melt outflow rate increases, and the energy that's removed with that melt outflow is proportional to that. Rho W is the density of water, and HF is the latent heat of fusion, the amount of energy it takes to go from liquid phase to solid phase. Then I've got a slide here that shows the shortwave radiation input. The model actually can take 3 forms of input. If you have measured net shortwave radiation, if you've got a net radiometer out over the study area, then it can bypass all the calculations and you can just take that. If you've got a measurement of the incident shortwave radiation, QSI, then you need to calculate the net shortwave radiation by using the incident shortwave radiation times 1 minus the albedo to account for how much is reflected. If you don't have the incident shortwave radiation, you can calculate it based on the transmissivity of the atmosphere, the solar constant, and this quantity that I've called HRI, which is the sort of hourly radiation index. And it's really an integral of the over a time step of the illumination of the sun on the snow, and that accounts for all the slope an aspect and perhaps shading behind mountain effects as the sun moves around. This is a whole few lectures in itself just to deal with solar radiation, so I'm going to skip over that. I don't know whether Mike wants to deal with that later on in the class, or have you done it already? You're going to miss it. You can do my physical hydrology class if you want to learn those equations in gory detail. The atmospheric transmissivity, when there's measured solar radiation, that's just calculated based on the measured solar radiation relative to what the solar radiation should be calculated from the sun angle on a horizontal surface, and then that atmospheric transmissivity is used to distribute that measurement out to other locations if you're applying the model in a sort of a grid distributed mode, and to account for the slope and aspect and the different illumination on different slopes and aspects. When the measured radiation is unavailable, we go through this procedure that calculates the atmospheric transmissivity based on the important quantity here is delta T, the diurnal temperature range. The assumption is that if the sky is clear, you're going to get a large diurnal temperature range. If the sky is cloudy, you're going to have a small diurnal temperature range. And this effect has been represented with this equation, and the parameters A, B, and C have been calibrated by these people, Bristow and Campbell. So you can, from the diurnal temperature range, get an estimate of how clear the sky is, and therefore how much incident radiation there is. We also need to talk about the albedo, and this is one of the slides that you saw last time that shows how the reflective properties of snow depend upon wavelength, and they also depend upon grain radius. And one of the things that happens with snow is as time progresses, the grain size increases. So you have a reduction in albedo. You notice the red line is for the smallest diameter grains, moving down to the yellow with the large diameter grains. So as snow goes through its metamorphism, the reflectance reduces. This is sort of a ugly, very busy, wordy slide, but it basically shows the equations, and I erred on the side of completeness rather than trying to just show the essence. I didn't want to reinvent the wheel on this modeling of albedo, so I just took a model out of Dickinson, 1993, that's used in the BATS land atmosphere model. And he has all these equations that look at the reflectance in the visible and infrared bands as a function of snow age. And he's got these R1, R2, R3, which represent the sort of growth of grain size. And this is a fairly empirical model, but it represents the decrease of albedo with time. This sort of effect that Mike spoke to you about last time, albedo decreasing with time. There's also an effect with albedo that, depending on the incident angle, if you have the sun just glancing off a snow surface, it tends to reflect more than if it's shining down vertically. Well, I'm not sure whether that's, maybe it reflects, I'm not sure whether it reflects more or less. I guess we could try and look at the albedo increases as the cosine of the angle changes. I don't remember the sense of that function, and it's hard to think on my feet and work it out, but one of you guys can can work it out. But basically, the amount of reflectance depends on the angle. So that's adjusted for, and these equations were, again, from the BATS model. So that's essentially the sort of the key elements of model. I've gone through in a fair bit of detail the sort of core parts of it. After we built the model, we wanted to try and calibrate it because there are parameters that are, well, we didn't know what the appropriate value was to put in there. We had things like the surface roughness of the snow, which the literature reports. We had the surface conductance, which was something that really just arose out of the way we were parameterizing surface temperature. There were albedo parameters. There was the melt outflow that was related to the saturated conductivity, where the literature sort of gives a large range of it. So we were able to obtain some data from the Central Sierra Snow Laboratory in California that's located just near the top of Donner Pass. And we went about trying to calibrate the parameters there, and then we tested the model at other locations to see how transportable it was. So I'll just show you some of those results from that calibration. And we sort of used a physical intuition-driven approach to calibrate it. We looked at the processes that we knew affected certain parts of the modeling process and adjusted the parameters pertinent to that. So for calibrating the surface roughness and the surface conductance parameter, those parameters play a role in the sensible and latent heat flux, which if you have measured net radiation, you can't change the radiation at all. So the only way you can change the sort of total energy into or out of the snow is by looking at the sensible and latent heat flux. So using the measured net radiation input, so looking at the dotted line here, we adjusted the Z0 as well as the surface conductance parameter that, I guess I didn't put that equation on here, to get this line, the light dotted line, to match with the observations as best we could. So we first calibrated those parameters. Then we also looked, I guess here's the equation that involves the surface conductance term. We also had measurements of surface temperature, and there's a depression of surface temperature during the night. Then the surface temperature, at least during this time step, was flat during the day when the snow's at 0 degrees C. We adjusted the surface conductance so that we sort of matched those depressions, which suggests that we are getting the right balance of conduction with this exponential sort of decrease of the penetration depth of surface fluctuations. So that's how we came up with surface conductance. Notice here that the observed temperatures actually go above 0, so we're never going to be able to match that. I'm not sure what it is about the instrument that Central Sierra Snow Lab was using that makes it measure temperatures above 0 on the snow surface. It might be, I think it's probably an infrared thermometer, and it might be reflecting infrared from the surrounding vegetation or from the sky and sun, something like that. I guess that does put a bit of question, and maybe that problem has also existed at night, and those nighttime temperatures are not any good. This is another time period where we also did the same thing. Then we calibrated those parameters all using the net radiation input. Now, this is the same slide I showed you earlier, except the arrows and annotation are different. Then we had one of the albedo parameters, and we drove the model with measured shortwave radiation incoming rather than the net radiation. So now the albedo calculations of the model are actually active, because if you're driving the model with net radiation, it's bypassing the albedo calculations. And we found by adjusting the one parameter from 0.95 to 0.85, we were able to sort of move from that line to this line down here and get a fairly good match to the observations. But notice one thing that I'll point out to you now. It seems like here we've got the observations are fairly flat, whereas the model has a bit of a gradient here. That gradient sort of reflects the fact that there's precipitation, snow is accumulating. It's a bit puzzling why the observations aren't showing that. And initially when I saw this, I thought, oh, well, that's just a small discrepancy between model and data. I'm not going to worry about it. It looks like the overall pattern is fine. But that sort of came back to haunt us later, and I'll show you how it did. Basically, the model, there's small amounts of snowmelt occurring here that the model is not representing, that we had to fix later on. Once we'd calibrated albedo, we went and then confirmed the difference between, or confirmed the agreement between the modeled net radiation when it's driven by incoming shortwave radiation, as well as the measurements of net radiation. So we're effectively testing the yellow highlighted parts of the energy balance equation. And then there's this melt outflow parametrization that said that the melt outflow is proportional to a saturated conductivity parameter and relative saturation. We adjusted this parameter so that you could get the sort of diurnal pulses of melt outflow matched between the model and observations. The melt outflow doesn't really play much of a role in the overall melt energy balance. Once water's melted, it's sort of going to pour out the bottom of the snow sometime, so this sort of diurnal pulsing is just really how rapidly the snow drains. And you can see that this lumped approach we've taken, where we don't worry about the sort of penetration of a surface wetting front, but we just say there's a bulk amount of water in the snowpack and the drainage rate is proportional to that, seems to work reasonably well. It does say that the melt starts a little bit in advance of where the observations recorded, because presumably that time lag is the time it takes from meltwater that's primarily generated at the surface to reach the melt collector. So it's not a perfect representation of the melt process, but it's reasonably good. So that was essentially the model calibrated. One of the places that we wanted to apply the model was in distributed hydrologic modeling. We'd built the model, we thought, sufficiently simple so that we could apply it on a grid over a watershed. And one of the first places that we went to do that was Upper Sheep Creek, which is in the Reynolds Creek Experimental Watershed. And I understand you guys are going to be going there sometime later in the spring. You may not go to Upper Sheep Creek. You're probably going to go to Reynolds Mountain, which is where they've got the sort of active research going on right now. But when we were developing this model, Upper Sheep Creek was a really active research site. So this just gives a 30 meter, actually 30.48 meter. They laid it out on a 100-foot grid over this watershed, and we applied the model in each grid cell. This is what Reynolds Creek Experimental Watershed looks like in the spring. There's large snowdrifts that accumulate on the lee side of each of the ridges, and as soon as the snow starts melting, it melts off the south-facing slopes and the places where the snow was thinner, and you're left with this sort of stripy effect of snowdrifts. So you've got a huge spatial variability in the snowpack, and that's important because it sustains melt late into the season. And now we've got a model that we're going to apply on a grid. We're going to have to try and estimate that. I guess this just shows Upper Sheep Creek, and you can see that there's a large snowdrift that appears. And if you guys go there, you'll see these trees are aspens that are probably 2 to 3 meters high. They're not really big aspens, but and they get totally buried every year with the snowdrift that forms behind the ridge. Later on in the spring, the snow's gone from everywhere. It's even started to get green, and there's still snow left. And this snow is essentially sustaining stream flow much later into the season than you would have had were this drift not there, and it's sustaining a vegetation ecosystem and I guess also a stream ecosystem. So the fact that you get these drifts forming is a real important part of the system, and we wanted to have a way to model that. The approach we took, I mean, there are wind-blowing snow models that have been developed, and I've collaborated with people sometimes on trying to do that. But the first approach we took here was the idea of trying to model the wind processes was, again, rather complex. So we said each location has a certain propensity to accumulate slow. If it's in a place where drifts form, that propensity is large. We're going to quantify that with what we call a drift accumulation factor. And we'll take the measured precipitation. If you look really carefully, there's a rain gauge somewhere in here, a shielded rain gauge that measures snow accumulation. We're assuming that the snow that accumulates in the drift is a factor multiplied by what's measured there. And these were the factors that we were able to come up with by basically comparing the measured rainfall to snow measurements on the ground. One thing I should indicate that was nice about this site, if we go back one page, you can see a few stakes here. There's actually stakes all around this watershed so that you can orient yourself. And they went and with snow tubes sampled the whole watershed on a really fine, well, on this 100-foot grid. So on 6 or 7 occasions through each winter, they would construct a map of the distribution of snow from manual measurement. So we were able to use those to estimate this drift adjustment factor that calculates the amount that you multiply the precipitation input by to say how much snow accumulates at each point. And then that's used as input to the model. And now we can run the model where we compare the observed snow water equivalent and simulated snow water equivalent. And you can also look at the basin averages, observed as 209 millimeters, modeled as 301. So there's a bit of a discrepancy there. Cumulative precipitation, 369. And as we this goes through the sequence of days when the survey was done. You can see how the model is keeping the snow in more or less the right place relative to the observations. Then later on in the season, the general snow cover starts melting, and you end up only with snow cover left in the drift areas.
The model results are from the wind blowing and running the snowmelt model? Right.
The model results are from running the snowmelt model with that drift factor as an input to multiply the snowfall.
Did you guys ever try to back out that wind accumulation factor using like prevailing wind speeds and topography? Or?
Yes, we did. I guess I don't have the results to show here, but there's a paper that I had a PhD student, Rajiv Prasad, work on. You've read that one. Okay, that looked at this area. It basically applied Glenn Liston's, what does he call his model? Snowtron or something.
Yeah, that's right.
Snowtron 3D. So we applied that. We had him apply that over here, and we tried to estimate the drift factors. We found that we didn't really get a good representation on a sort of a cell-by-cell basis. But when you looked at the sort of distribution overall, it was reasonable. So here these things go on middle of May, late in May, even later in May, and that's the end of the Reynolds Creek work. Now I'm going to talk a little bit about about an experiment that I did here in Cache Valley. I guess this location 1, which is the USU drainage farm. It's just near Campbell Scientific, just south of Logan Airport, sort of west of where we are here, to look at snow processes, to look at how well the model was working. And one of the things I really wanted to get at with this experiment, which I didn't really get at, but I discovered some other interesting things, was the sublimation, how much water is actually lost to evaporation. So this shows our experimental setup. So it's nice, controlled environment, flat, large distance, unlike some of the mountainous places we might have worked. And this was a site that had been used for studying of evaporation fluxes by the Biological and Irrigation Department. So I sort of piggybacked off their instruments. They had these infrared thermometers that measured surface temperature. They had temperature and humidity probes inside of these radiation shields, so you can measure a profile of temperature, and I guess this was the profile of humidity. You can see there's some wind anemometers measuring a profile of wind speed. On these stakes here, you can't see it in the photograph, but there's fishing lines strung between that every 75 millimeters with thermocouples on the fishing line. So we measured the sort of profile of temperature within the snow, and it's from those measurements that we actually got the sort of most interesting results. They are also associated around here, sort of at the back there, net radiometers measuring radiation as well as incoming radiation, I guess, measured on this thing. No, that's the irrigation pipe in the back. I guess on this pipe here, there was a incoming radiation measurement. We pointed some up and some down to try and get at the albedo. It was a learning experience for me. This was the sort of first field experiment I ever tried to do. This shows my graduate assistant, Hydrology Chattopadhyay, and we were trying to keep track of the sublimation. Beneath this, there was a weighing lysimeter, basically a 1 meter square block of soil that was isolated from the rest of the soil, and it had load cells beneath it that was used in the summertime to measure evaporation by looking at how the weight got less as evaporation occurred. Well, we thought, oh, great, we can use that in the winter to study the same thing. But we were concerned about the snow bridging between the load being carried by the lysimeter and the surrounding areas. So we would go every time there was a snowfall and span this ladder across it and saw around the edges with a saw to try and make sure there was no bridging, and the weight of stone being measured was only the snow on the lysimeter. So that showed it sort of after we'd sawn it, and I guess there was some disturbance because there's a crease there, but I guess you can't measure anything without disturbing it. Who was it? One of the famous physicists figured that out. And then this is just looking at some of the data logger setup that we had recording all the thermocouple instruments. And another shot of the site with well saws in the background. So these are some of the observations that we were able to get there. We recorded, I also dug snow pits and recorded the density of snow and measured the depth. So we were able to estimate water equivalent, and we applied the model, and we got the similar sort of results as we've been getting elsewhere. The modeled and observed snow water equivalent seemed to be working fairly well. We only started it halfway through the season because I guess we were late getting the instruments in, and we were sort of putting the last instruments in while the snow had already arrived. So we couldn't start at the beginning of the season. This shows some of the data we got from the temperature profiles measured through the snow. We had a thermocouple beneath the ground, a thermocouple at the snow surface, and then thermocouples at various heights above. So you could see what the temperature profile was, and you can also see how as the air temperature changed, I guess this is 3 a.m., 6 a.m., 9 a.m., 12 noon, so we were going through a warming phase. Then 3 p.m. it was still warming, I guess 3 p.m. was that one. Then 6 p.m. it got colder. Then for some reason that night it got warmer, 9 and 12 at night. But there's that sort of change of air temperature, and you can sort of see the fluctuating back and forth of the temperature within the snow, trying to keep the surface temperature similar to the air temperature. We were able to also plot time series of the temperatures at different depths. So you can sort of see the large fluctuations in snow surface temperature that were recorded. These are the infrared thermometers relative to and then as you go down with depth, the fluctuations get less and less. And also, if you look carefully, you'll see that there's a bit of a slant to the right, so they are lagging each other. From that data, we were actually able to calculate the energy content, because you've got temperature, we've got density of the snow, we know what the heat capacity of ice is, so we can calculate the energy content. And lo and behold, we got bad news. This was the energy content that we calculated from those temperature measurements, and there's a little bit of jiggle to it because there was uncertainty in the temperature measurements. And this is the energy content we get from the model. And the model is saying it's way colder than, the snow's way colder than we're recording it. So we discover a problem. We calibrated the model against Central Sierra Snow Lab. We hadn't had this sort of information. We had every indication everything was working correctly, but it really wasn't. So what are we going to do about it? So I had another graduate student look at what's actually going on with conduction into the snow and see if there's perhaps a better way of parameterizing the surface temperature fluxes and the heat fluxes involved. So we looked at the sort of simplification of the heat equation with the rate of change of temperature with time being proportional to the second derivative of temperature with depth, and that thermal conductivity parameter being related to the sort of thermal diffusivity and heat capacity and density. We looked at the equations involved in this exponential decay, assuming you've got a sinusoidal fluctuation at the surface. And we were able to come up with some different options for modeling the surface temperature. The option we were really using was the sort of gradient-based approach, which said the conduction was a gradient between the surface temperature and the average temperature of the snow. It turned out this forced restore approach is widely used in the sort of atmospheric community. It was originated by Diurnal, and basically they have the same problem. So we used this forced restore approach, which looks not only at the temperature gradient between the surface and within the snow, but the rate of change of the temperature gradient. If you go back up here, one of the things that comes out of this differential equation is you've got a rate of change of time with the surface temperature. And then we had a sort of a modified forced restore approach that looks at daily cycles as well as longer term fluctuations. And basically, to make a long story short, I'm not going to go through all the details of that. We came up with a new way to represent the conduction of temperature into the snow, and we also fixed a few other things that had been sort of going wrong and offsetting the model that made the sort of errors compensate, at least in terms of modeling snow water equivalent. And these are some of the results that we get comparing the model initialized at different times versus the observations. Now suddenly the model's a lot more sensitive, and it tends to want to melt the snow a lot more easily because the energy content is not so low. The snowpack's not being kept so cold anymore. So the model has a sort of a tendency to sort of run off and melt too early sometimes. But we were able to identify all the times when it occurred was basically times when we were unsure about our data, where there was an extremely strong wind and we weren't able to record well the snowfall because we had an unshielded rain gauge. And so we weren't sure what's going on. So we would then reinitialize the model after that, and then after that, and after each of these occurrences in it would tend to model the meltout following that. And these are some of the parameters that had to be adjusted to get the model to work with the revised conditions. Now this shows the energy content, the observed energy content being the black line, and the modeled energy contents. Now you might, just looking at that, be able to say, well, hey, you guys are not doing any better, because here you've got a modeled energy content up at 3,000, whereas observed energy content is 0. Can anybody tell me whether that's good or bad? Well, our observed energy content is measured with thermocouples in the snow. It's not really measuring energy content, it's measuring temperature. The energy content state variable accounts for the liquid water in the snow. So as soon as the snow starts melting, that's when the energy content is positive. The thermocouples are going to tell you that the average temperature is getting close to 0. Remember, this is an average of all the thermocouples. So we are unable with the thermocouples to measure positive energy content, but we are able to measure negative energy content. So one needs to look at this graph for these points here where the energy content is negative. When it's positive, as long as this is close to or at 0, the model is still working okay. Then we went back and applied it to our Central Sierra Snow Lab data. And remember I showed you that graph before where there was the sort of departure here during the accumulation phase. Now suddenly the model is actually keeping track of that small amount of melt that's occurring during the accumulation phase. And it's following the actual data much more closely. So that was a nice sort of present that we got from having done all this work to fix the model. And I guess if we again look at the accumulative melt, the early model was not representing any accumulative melt in the early part of the season. Now the model is. We also went through the sort of comparisons of meltwater outflow, which weren't really dramatically affected by the fixes, and surface temperature comparisons. So that's all that I have about the sort of science of the way the model works. And I guess I've just got 4 slides left that talk about how to use the model. They're just really procedural. I don't know whether, Mike, are you going to have them do an exercise where they actually try to use the model? You probably want to look at the manual that we have for it, and this is my well-worn copy, that is on the website. And the information I've got in these next slides is just abstracted out of the back of that, which says Guide to Using the Model. There's 4 input files the model takes. The weather file, where you give it the information at each time step, the precipitation, temperature, humidity, wind speed, and radiation. There's the model parameter file, where you give it all the parameters. So you can actually change the parameters if you want. The site variable file, where you give it parameters that describe the specific conditions to that site. And then there's a diurnal temperature range parameter file that gives the average diurnal temperature ranges for use in the sort of Bristow-Campbell approach for calculating the atmospheric transmissivity. And that's only used if you don't have measurements of incoming radiation. But you need to give it the file anyway, because the code is not clever enough to know whether to use it or not. So we just always give it a file. If you're running in the mode where it's not going to be used, it doesn't matter what the numbers in the file are. So this gives an example of what the weather file looks like. The first row just sort of says the the starting conditions, the month, the day, the year, the hour that the run needs to start at, the time step, the initial energy content. So you can see this is a run that's starting in May, and we're giving it a fairly large initial energy content. So the assumption is that the snow is already melting. You might say, how do I get that number? I probably got that number because this was a run. We ran the model up to a certain point in time and looked at the results and then wanted to start it later on. So we were just starting it from where it stopped off. The initial snow water equivalent, and there's a dimensionless age parameter that's involved in the albedo, or dimensionless age state variable that's involved in the albedo calculations. So the model really has three state variables: the energy content, the water equivalent, as well as the sort of surface age of the snow that's used in the calculation of albedo. It does allow you to skip some time steps at the beginning. So you can specify that you want to skip over some time steps so that you don't have to, if you want to start it later, you don't have to edit that data out of your file. Here that's set to 0. And then there's columns of data that give air temperature, the precipitation rate during that time step, the wind speed during that time step, the relative humidity as a fraction, the daily air temperature range, so the difference between the maximum and minimum. Those are all the same because it's one day, I guess the 6-hour time step, so there's 4 time steps a day. Then the next day had a smaller daily temperature range. Then the incoming shortwave radiation and the net radiation. Now, the model is set up so you actually have to give numbers here, and then you can tell it whether to use the incoming shortwave or to use the net radiation, or to just assume that that data is not available and calculate the shortwave radiation based on the daily temperature range. But numbers still need to be in the column. If you don't have the numbers, you can just put zeros or anything you like there, and the model will not use it if you tell it to use the option that doesn't require them to be used. Then there's the parameter file that really just gives numerical values for all the parameters involved with the model. Many of these you can think of as almost being physical constants. They're not parameters that you would typically want to adjust. But, for example, the temperature above which all precipitation is rain, the temperature below which all precipitation is snow, those come out of an Army Corps report. And I guess they've been changed a little bit because I converted from Fahrenheit to C and I rounded them. And then between those temperatures, there's a sort of linear interpolation. So if you've got 1 degree C, the assumption is that half of the precipitation is rain and half of it is snow. Freezing point, you'd never want to change that. The conversion between Kelvin and degree C, you'd never want to change that. Emissivity of snow, you might want to change that a little bit. Stefan-Boltzmann constant, you never want to change that. Heat of fusion, heat of vaporization, water heat capacity, ice heat capacity, these are basically all physical constants. The ground heat capacity, that might depend on the type of soil you have, how much organic material is in it. Air heat capacity, that's again pretty much a physical constant. Ideal gas constant, von Karman's constant. The nominal measurement height for air temperature and humidity. The calculations for the turbulent fluxes assume air temperature is measured at a certain height. So if you're measuring, you should put the height that you're measuring stuff at. Then the surface aerodynamic roughness, you may want to change this. This was one of the parameters we calibrated. The factor to convert hours into seconds, that's pretty much set. Density of ice, density of water. Snow density, this you may want to adjust. Soil density, again, there's a site-dependent condition. The liquid holding capacity of the snow. The saturated conductivity, this was the value that we calibrated, but it was within the range that you get in the literature. So and so on. So you can see these are the parameters that are in that param.dat file. Then there are site variables that are specific for the site that you're applying it to. the forest cover fraction, the drift factor, a number that represents how much the precipitation is multiplied by. If you're applying this on a grid over a watershed, that might be different for each grid, as we did for Upper Sheep Creek. The atmospheric pressure at the location that you're at. I guess we don't worry about the sort of weather patterns, because atmospheric pressure is only, well, it's just it's a constant in front of the equation, so the small fluctuations with changes in weather don't matter for this model. So you can just put a standard atmospheric pressure in. A ground heat flux, that needs to be input for each site. An albedo extinction parameter, that's related to the sort of shrub height, because if you've got vegetation penetrating through the snow, it reduces the overall albedo. So that's why we put it in the site variable parameter. And then the slope and the aspect, I guess, I don't know why there's only two numbers here, and it says slope, aspect, and latitude. I think that this 0 is supposed to actually be wrapped around there. So it's 1, 2, 3, 4, 5. So this was 0 slope. That was the aspect, which becomes irrelevant if the slope is 0. And the latitude, which is used in the solar radiation calculations. Then the diurnal temperature range file just lists the average diurnal temperature range associated with each month, and it also lists the default parameters A and B that Bristow and Campbell arrived at, and you could change them if you wanted, but I wouldn't know how to change them, so I've always run with the same numbers. And that was it. I'd be happy to answer any questions.
Maybe just escape out of there.
Probably see if anybody's been chatting, or if they've all... how do I get to see the chat? Nobody's said a thing.
This is a 10-second delay.
Okay. Yes.
Your ground heat flux, when you ran your model up in the Reynolds Creek experimental area, did you hold that constant the whole time, or?
Yes, we held it constant the whole time. And that's probably not necessarily the best thing to do, because ground heat flux does decrease as you progress through the season. It's a sort of a small effect, and you have to make some simplifications. We didn't get round to adding any additional complexity in terms of ground heat flux.
But in the looking at all of the magnitudes of each of the components of the energy balance, that's a pretty small magnitude generally.
The ground heat flux is generally pretty small, but it turns out if you leave it out over the whole length of a season, it can lead to a significant error. So you don't really want to admit it, because it's always in the same direction. The sensible and latent heat flux is sort of a positive negative, whereas the ground heat flux is always the small positive number from the bottom. I guess what you also have to be aware of is that the ground heat flux, I didn't even look at whether the light's on. I guess somebody would have complained, or if they couldn't hear me. The ground heat flux, what was it? Where was I going with this?
Ground heat flux, has it changed through the winter? Significant? I thought it was a significant magnitude.
I've lost my train of thought where I was going with that.
Well, it's likely going to matter when you have at the very beginning of the season anyway, when you don't have very deep depth of snow.
Oh yes, I guess the ground heat flux that we're talking about is the ground heat flux at the bottom of our thermally active soil layer. So it's maybe 20 centimeters down or 40 centimeters down. When first we constructed the model, we said we were going to group 40 centimeters of soil. We're going to say that's interacting with the snow. The idea being, if you have snow fall on warm ground, the heat from that soil will get added to that snow immediately and cause that to melt, and that's what happens to this. Many times, what happens to the first snowfalls that we get. Later on in the season, that soil has become cold, and snow falls on frozen ground. There's no heat to absorb from the ground, so it doesn't melt. And the ground heat, the bottom of our control volume that is our model is the bottom of that DE, which initially we used to always run it as 40 centimeters. Lately we've started running it at 20 centimeters because we found that when we made some of these changes to fix the surface temperature parameterization, and we started looking at those temperature fluxes, the ground temperature never really became the same as the snowpack. The ground temperature was always quite a lot warmer than the snowpack. So we thought that keeping track of 40 centimeters of soil and assuming it's the same temperature as the snowpack might be contributing to our energy balance problem. So we've sort of been running with it either 20 or 10. The reason we have it there at all is to give the model some numerical stability, because if you have otherwise, you can have the energy content going to zero sort of at the same time as the water equivalence goes to zero, and you end up with a sort of divide by zero problem, and you have a whole lot of numerical work you have to do to get that to work out right over a really itty-bitty irrelevant problem when you've got 5 millimeters of snow left.